Imagine if a meteorite the size of a school bus were to strike the Earth. What would happen? Let's examine this hypothetical scenario in this episode of Imagine If. To begin, it's crucial to comprehend the nature of meteorites and how they interact with our planet. Meteorites are fragments of asteroids or comets that survive their passage through the Earth's atmosphere and land on the surface. They vary greatly in size, composition, and frequency of impact. A school bus typically measures about 40 feet, 12 meters in length, and weighs around 15 tons when empty. However, a meteorite of similar size would be significantly denser, composed mostly of rock and metal, particularly iron and nickel. The density of such a meteorite could range from 3,000 to 8,000 kilograms per cubic meter, making its mass anywhere from 10,000 to 50,000 tons. As the meteorite approaches Earth, it would travel at astonishing speeds. The average impact velocity of meteorites is about 20 kilometers per second, approximately 45,000 miles per hour. At such speeds, the kinetic energy, the energy of motion, is immense. If we assume a mass of 25,000 tons, or 25 million kilograms, and a velocity of 20 kilometers per second, the kinetic energy upon impact would be equivalent to about 12 megatons of TNT, nearly the size of a modern nuclear weapon. As the meteorite enters the Earth's atmosphere, it encounters air molecules, leading to frictional heating. This process causes the outer layers of the meteorite to heat up and vaporize, a phenomenon known as ablation. The meteorite becomes enveloped in a bright plasma glow, creating a spectacular fireball visible over vast distances. The intense heat and pressure can cause the meteorite to fragment or even explode before reaching the ground, an event known as an airburst. The altitude at which this occurs depends on the meteorite's composition, angle of entry, and structural integrity. Iron meteorites are more likely to reach the ground intact due to their strength, whereas stony meteorites may disintegrate at higher altitudes. If the meteorite were to explode in the atmosphere, the resulting airburst could be devastating. The shock wave from the explosion would propagate outward, causing damage over a wide area. The 2013 Chelyabinsk event in Russia is a prime example. A 20-meter-wide stony asteroid exploded about 30 kilometers above the ground, releasing energy estimated at 500 kilotons of TNT, about 30 times the energy of the Hiroshima atomic bomb. The Chelyabinsk airburst resulted in over 1,500 injuries, mostly from shattered glass due to the shockwave breaking windows. Buildings were damaged, and the event served as a stark reminder of the potential hazards posed by small asteroids. In our scenario, the meteorite is larger and possibly more massive than the Chelyabinsk object. If it explodes in the atmosphere, the energy released could be several times greater, leading to more extensive damage. The shock wave could flatten structures, and the thermal radiation could cause fires over a wide area. Alternatively, if the meteorite survives its passage through the atmosphere and impacts the Earth's surface, the effects would be even more pronounced. Upon impact, the kinetic energy would be transferred to the ground, generating an explosion equivalent to several megatons of TNT. The immediate aftermath would include the formation of a crater. The size of the crater depends on various factors, such as the meteorite's mass, velocity, angle of impact, and the geological characteristics of the impact site. Using scaling laws from impact crater studies, a meteorite of this size could create a crater approximately 500 meters in diameter and 100 meters deep. The impact would eject a massive amount of material into the atmosphere, creating an ejecta blanket around the crater. Debris could be thrown kilometers into the air, raining down over a wide area. The shockwave from the impact would cause catastrophic damage to structures within a radius of several kilometers, potentially leveling entire cities if it struck a populated area. Seismic waves generated by the impact could be equivalent to a magnitude 6 or 7 earthquake, depending on the impact's energy and location. These seismic waves could cause further structural damage over a larger area and might trigger landslides or tsunamis if the impact occurred near or in a body of water. Speaking of water, if the meteorite were to strike an ocean, the consequences would differ but remain severe. The impact would generate massive waves, commonly referred to as impact tsunamis. These waves could travel across ocean basins, affecting coastal regions far from the impact site. In addition to physical destruction, the impact would have atmospheric effects. The dust and aerosols thrown into the atmosphere could affect climate on a regional scale. Sunlight could be temporarily blocked, leading to cooling in the affected areas. Acid rain could result from the vaporization of minerals and release of sulfates, impacting ecosystems and agriculture. Historically, we can look at events like the Tunguska explosion in 1908. An object estimated to be about 50 meters in diameter exploded over Siberia, flattening an estimated 80 million trees over an area of 2,150 square kilometers. The energy released was equivalent to 10 to 15 megatons of TNT. Remarkably, due to the remote location, there were no confirmed human fatalities. Such events are rare but not unprecedented. Earth experiences a constant bombardment of space debris, most of which burns up harmlessly in the atmosphere as meteors. Objects larger than 10 meters in diameter impact Earth roughly once per decade. Most fall into oceans or uninhabited regions, going unnoticed. Current efforts to detect and track near-Earth objects, NEOs, focus primarily on larger asteroids, those capable of causing global or regional catastrophes. NASA's Planetary Defense Coordination Office, PDCO, and other international organizations are working to catalog and monitor these objects. As of 2021, over 25,000 NEOs have been identified, but smaller objects, like our hypothetical meteorite, are more challenging to detect due to their size and the vastness of space. If such a meteorite were detected heading toward Earth, the time between discovery and impact might be short, possibly days or hours. The small size and high speed make early detection difficult. In such a scenario, emergency response would focus on evacuation and public safety measures in the predicted impact zone. Technological solutions to deflect or destroy incoming meteorites are currently in development, but are primarily geared toward larger asteroids. Missions like NASA's Double Asteroid Redirection Test, DART, aim to test our ability to alter an asteroid's trajectory. For smaller objects, especially those detected with little warning, these methods may not be feasible. From an ecological standpoint, the impact could devastate local wildlife and habitats. The immediate area would be rendered uninhabitable, and recovery could take years or decades. If the impact were in a sensitive ecosystem, the loss of biodiversity could have lasting effects. On a global scale, the impact would likely not cause significant long-term climatic changes. Events capable of triggering mass extinctions, like the asteroid impact that contributed to the demise of the dinosaurs 66 million years ago, involve objects several kilometers in diameter, releasing energy billions of times greater than our school bus-sized meteorite. Astronomers and scientists continue to advocate for increased funding and research into NEO detection. The use of ground-based telescopes, space-based observatories, and advanced software algorithms enhances our ability to detect smaller objects sooner. In conclusion, a meteorite the size of a school bus striking Earth would be a significant event with serious local consequences. While it wouldn't pose a global threat, the impact could cause substantial damage and loss of life in the affected area. It underscores the importance of ongoing efforts in space observation and planetary defense. reminding us of our planet's vulnerability to cosmic events. If the meteorite were to strike a densely populated urban area, the consequences would be dire. Buildings within the immediate blast zone would be destroyed or severely damaged. Modern skyscrapers, although designed to withstand significant forces, might not endure the shockwave and seismic vibrations of such an impact. Emergency services would be overwhelmed, and hospitals could become inoperable due to structural damage or loss of power. The disruption of critical infrastructure like power grids, water supply systems, and communication networks would exacerbate the disaster. Without electricity, coordinating rescue efforts would become challenging. Water contamination could occur if pipelines burst or if debris infiltrates reservoirs, posing public health risks. While the physical impact of a school bus-sized meteorite would be localized, the ripple effects across various facets of human life would be profound. It highlights the interconnectedness of our modern world and the importance of comprehensive planning and international cooperation in facing such universal challenges. If you found this exploration thought-provoking, please hit the like button and subscribe to our channel. We release new episodes every Friday evening, so stay tuned for more intriguing Imaginiftum scenarios. Thank you for watching, and keep imagining the possibilities. Please let us know if you have a question you would like us to try and answer.